Hi all. In today's lecture, we'll be talking about the Poisson distribution and also finding the moment generating function and hence its mean and variance. Okay. So, what is a Poisson distribution? Actually, it is a discrete distribution where we can take a random variable x to be discrete, and it's going to follow the Poisson distribution. Then its probability mass function is given as e to the power minus lambda power x by x factorial, but x runs from 0, 1, 2, 3, etc. up to infinity, and lambda is a parameter which is greater than 0 here. All right, now let us try to understand how to find the moment generating function. Mx of t is given as expectation of e power tx. You can write this as sum of e power tx into probability of x equal to x, where x runs from 0 to infinity. And then now you can substitute probability of x equal to x here. What is the formula? E power minus x lambda per x by x factorial. Then you can just try to understand this. You can pull this e power minus lambda outside. Therefore, you have e power t. This one I will write as e power t power x, and this one is as such. Okay. Now these two terms are having the powers x, so you can just club this together. So it will be lambda e power t power x. So that is what written in the next step. So once from the previous step you got this step. Okay, I mean lambda e power t power x. Now you just expand the summation, put x value 0 here, x value 1 here, x value 2 here, x value 3 here, like that it runs. So once we expand this, the first term will become 1 because 0 factorial is 1 and anything power 0 is 1. Whereas the second term you have e power lambda e power t by 1 factorial, third term lambda e power t whole square by 2 factorial, like this. But we know very well that 1 plus x by 1 factorial plus x square by 2 factorial plus etc. is nothing but e to the power x. So you can just compare this terms with your x terms. So this is also looking like 1 plus x by 1 factorial by x square by 2 factorial, like that. So this could be written as e power x, but x is nothing but lambda e power t. So I think this is clear for you. Now when the base is same, you can add the power. So e power minus lambda plus lambda e power t. So you can pull out like we can just take lambda common, which can be written as e power t minus 1, or usually we will represent with the negative power. So e to the power, pull minus lambda out, it will be 1 minus e power t. So your moment generating function is e to the power minus lambda into 1 minus e power t. So this is the moment generating function. Now from this, how will you obtain the mean? You know very well, when you differentiate moment generating function one time with respect to t and put t equal to 0, that will give you the mean. So you just try to take this term. Okay, again you can split it. This looks like e power minus lambda plus lambda e power t. Now you have two terms in this. Just try to split and write in multiples. Right. So why we do this? Because you don't have t in e power minus lambda, which is independent of t. Therefore, we have to differentiate only this term. So this part I am just taking it and putting it in the differential operator d by dt of mx of t. All right. So that will give you mx dash of t. So what I will do, I'll just pull this term out. Okay, and then I will differentiate only this term. So what is the differentiation of e power lambda e power t? That is e power lambda e power t into lambda e power t differentiation is lambda e power t. Okay, so also you have one e power minus lambda outside. Now these are the three terms which is there in mx dash of t. Now in this you can put t equal to 0. I mean in mx dash of t, you replace t by 0. So wherever t is there, you replace by 0. You get e power minus lambda, e power lambda e power 0, lambda e power 0. So this will become 1. This will also become 1. So you have e power minus lambda, e power lambda, lambda into 1, which will be lambda. So this is nothing but your mean of x, which is the uh, mean of Poisson distribution. Okay, e of x equal to lambda. Now coming to the part of variance, variance could be calculated by using this formula e of x square minus e of x whole square. But how will you do that? First, let us find e of x square. So when you want to find e of x square, you have to differentiate your mx of t two times, and then you have to substitute t value as 0. So that will give you mx double dash of 0, and that will give you the e of x square or mean square value. So mx double dash of t, you're going to differentiate mx dash of t with respect to t. So mx dash of t, already you know it is here. This one I am just taking it and putting it in the differential operator d by dt of this terms. Again, you can find this term and this term are independent of t, so you can just take this two terms outside of your differential operator. So take it out, so you will get d by dt of e to the power minus, sorry, lambda e power t into e power t. That is alone present here. Now once you have this, this looks like your uv method, so you can apply u dv plus vd. Okay, so I'm just keeping this term as such and differentiating this term. Okay, I'm differentiating this term, plus I'm just keeping this term as such and I'm going to differentiate this term. So when I differentiate this term, this will be e power lambda e power t into lambda e power t. Okay, so that is the only terms which will get be extra in this place, whereas here in the first term it is as such. Okay, so our objective is to write this term with t equal to 0. So this is our mx double dash of t. So when you want to put t0, that will give you the mean square. So wherever t is there, you put 0. So what will happen here is, like, you can see mx dash double dash of 0 is lambda e power minus lambda into e to the power lambda e power 0 into e power 0 plus e to the power 0 into e to the power lambda e power 0 into lambda e power 0. So all this e power 0 will be 1. So leaving out those terms, without that, we will write this first term, this term is 1, this term is 1, this term is e to the power lambda, this term is lambda, this term is 1. Okay, so we have written like this. Now this term e to the power lambda plus lambda e power lambda you will get. Okay, and now finally you multiply lambda e power minus lambda with e power lambda first term plus lambda e power minus lambda with lambda e power lambda second term. So that will give you lambda e power minus lambda e power lambda plus lambda square e to the power minus lambda into e to the power lambda. And you can know that the exponents with negative powers, with the same negative powers, negative and positive powers, that will be getting cancelled. So this will be 1, so you will get lambda here. This also be cancelled, which is 1, you get lambda square. So this is your e of x square. Okay, and that is what we have written here. Okay, e of x square. Okay, we got this answer. All right, so now this part is clear. Now let us find the variance. The formula for variance is e of x square minus e of x whole square, and we know e of x square, which is nothing but this term. Okay, we have to plug in here, and e of x is nothing but lambda whole to the power 2, so that means e minus lambda square. So this gets cancelled, leaving out lambda. So the variance is nothing but lambda. Okay, so thus we form the relationship between mean and variance in Poisson distribution. Of course, it's quite interesting. Both mean and variance is going to be lambda here. That is same. So that is the relation of Poisson distribution. All right.